All right, good morning, everybody. Welcome back to geometry. We've got some fun times ahead. And speaking of ahead, today's quote is a reminder to keep moving ahead, no matter what may come in your way. Okay, you can do it. Believe in you. And for the new topic, let's open up yesterday's work and check some of our answers there. And I think on some of these, we will realize, hey, wait a minute, these weren't as simple as I hoped they would be. What's going on? Okay, we'll run through them together here. All right, so first up, volume of prisms and cylinders. They seem so straightforward, don't they? Right triangular prism, find the area of the triangle, multiply by the height. And but they've set a trap for you here. This 10 is completely useless. This is the hypotenuse of my triangle. It says it's a right triangle, so I have to believe them and assume one of these angles, it wasn't marked, had to be 90 degrees. The only one that makes sense would be up here. This guy is like definitely very looking acute. And they tell me that this is 6 over here, which is going to be the same length there. So if I drag that over, now I have a 6 by 6. And that I can use and find the area of my triangle and thus the volume of the whole prism. Number 2, though, number 2, it seems so simple. Like, okay, trapezoid, got it. You get the average of the two bases times the height. Okay, well, once again, drag your 6 down. It matches over here, 6, 3. What's the height? They don't tell me the height. They've got this extra 5 out here. That's not the height of the trapezoid. Okay, if you used that 5 in your calculation, that would be wrong. You would not end up with the correct answer. We got to use a sneaky little trick here. I'm going to draw in an extra line here. And this only works because it's a right trapezoidal prism. I can draw another line and make this also at a right angle. Okay? Remember, you're allowed to draw extra lines. I believe I mentioned that once before. And when you do that, now this 5 becomes the hypotenuse of my triangle. And if I know this base is 3, that means up here this much is 3. 6 minus the 3 leaves me 3 for this side of my triangle. Now, we will talk more about the Pythagorean theorem next week, but many of you may have seen it before. So I don't feel too bad for having this left on here. Right? I definitely crossed out the ones with the regular hexagons. That you need stuff you've probably not seen before. But the Pythagorean theorem, real quick, says that that long side, that hypotenuse, is equal to the 2 legs squared. The square of the hypotenuse is equal to the sum of the squares of the 2 legs. And so knowing this was 5 and this was 3, we could solve and figure out that this would have to be a height of 4 for my trapezoid. And thus I can get the area of the trapezoid multiplied by the height of the whole prism for 144. A little bit more involved than we may have expected. All right? But that's what makes it such good practice. All right, we're skipping 3. So let's come down to 4, 5, 6 now. Okay, these ones did not require any special additional knowledge here other than treating things algebraically. Don't get so caught up in plugging the numbers in that you forget how to manipulate them when it's still variables. Okay, so this is just a simplification. Right? 4y times x times 2x plus 3, distribute that. There you go. Here's simplified cylinder there. Notice they give you the circumference, not the radius. Okay. And again, the box here, the rectangular prism plus the half cylinder. The most simplified form would be to factor out the x squared y from each of those pieces. But if you have this as 6x squared y plus 3x squared y pi, then you'd be correct as well. All right, and then number 7 is a set of, break this into rectangular prisms. It should be pretty easy, except if you missed that the units change. These are in inches, this is in feet. They wanted cubic feet, so make sure you do your unit conversion there. That said, any remaining questions on the first page? All right, then on to the next page. Pyramids and cones. Okay, first one, square base pyramid. We know the height as given. Straightforward, you can do that one with the formula. Number 2, that right hexagonal pyramid. Oh, we're going to need more information to deal with the hexagons. We'll come back to that next week for sure. That takes some special triangles, not just regular Pythagorean theorem. Speaking of Pythagorean theorem, this guy also may have thrown you off because you weren't given the actual height. You were given the slant height. Okay? I warned you, watch what they actually give you and what you actually need. They're not always the same thing. This whole distance, 14, half of that would be 7, which you needed to find anyways. And this is another Pythagorean triple, 7, 25. Solve for 24 there. We'll come back and practice those some next week. Well, same thing with number 4. You need to multiply the perpendicular lengths here so you don't have this one. So don't use that 25. You need to actually get the 24 here and then multiply by the 30x, including your halves every time to get 840x cubed. 5 is just 2 cones. And number 6 is actually a cone. They just hide it from you by saying, oh, it's a triangle that we're going to spin around the axis. Right? So if you imagine you spin it fast enough, it will blur out and appear as if it was a cone. And keep that in mind in the back of your head. Calculus loves doing these things. I don't know where it came from originally, but they like taking stuff and revolving it around an axis and finding the volume and such therein. So that'll be a common trope coming up. And then finally, 7, 8, 9, the find volume and compare. Turns out that this cone is in fact bigger than this cylinder. Okay? You lose a lot of volume from being a cone, but they made the dimensions big enough, bigger. These two triangles, it's not quite a prism, right? Because it's like a triangle of a triangle. So you got to half it and then half it again. But they have the exact same dimensions. There's one of them is just flipped and rotated around. So since no units were specified, I'm just using u cubed, units cubed there. And then number 9, this is the most interesting. The 3 separate cones versus one great big cone. Because notice my radius on each of these cones is 3, and I have 3 of them. So 3 radii would be 9, 3 times 3. So I have one big cone with that whole radius, 9. What happens if you were to combine them all and make one great big one that seems to be the same size? You would think, okay, if I have 3 3s, that makes 9. That should be the same. But no, it is way bigger, okay? Because that triplication gets multiply it again. This isn't just 3 times bigger. It's 3 times long and 3 times wide. Right? You got radius squared in there for that circle. Okay. Any questions on the second page? All right, then let's take a look at today's work. Volume and surface area of a sphere. Now, these questions really are not that bad. I have checked and double-checked. You don't need anything else here except a little bit of circle knowledge when it comes to the fractions. We'll get there. So when it comes to a sphere, the volume and the surface area are very related. Okay, sphere is a 3-dimensional circular object, so of course we're going to have radius. Of course we're going to have pi. Okay, those are going to be involved in both of those. The surface area, though, is only 2-dimensional. Even though it's now on a round object, we're talking about the 2-dimensional coverage, versus volume takes up 3 dimensions, so we get r cubed there. And so then it's just a matter of what any coefficient or fraction is involved. And it turns out the surface area is going to be 4 times pi r squared. And the volume is 4/3 pi r squared. So the volume should kind of remind you of the cone and the pyramid, right? Where we had to reduce it by a fraction there. So we've got that 1/3 going on. Okay? But we're going beyond just a single circle. We're wrapping in 3 dimensions here. And so why exactly 4? That's a derivation for another day. But just kind of understand the relationship between the two. Always have the pi's and the r's to the power of, well, what dimension are you in? Are you measuring? Okay? And if you leave that 4 up front, and remember that volume is 1/3, you'll be all set. Okay, but again, not an equation you have to memorize. This volume one is given to you on the SAT formulas. The surface area is not. Okay, so that would be the thing to remember, is the relationship between the volume and the surface area. I would commit that to memory. Instead of maybe from whole cloth, say, okay, if I know the volume one, I can just copy it and just take out the 1/3, reduce the cube to squared, because I'm in only 2 dimensions now. But with those 2 formulae, you will be all set to answer these questions. We've got volumes of spheres and fractions of spheres. Okay, this might take a little bit of visualization. This is a full sphere. It's the whole ball there. Okay, here you ever seen one of those cutaways where they cut a baseball in half to see what's on the inside? Yeah, here you go. Or those of you that have a grapefruit for breakfast in the morning, there's your grapefruit there. Okay, this is half of a half. Okay, here we've got a chunk taken out of the top half. And they tell you how much of a chunk. That's 90 degrees out of the 360 degrees it would have been all the way around. So I'll let you figure out what fraction that is. Okay, this is what fraction of that upper hemisphere, and then that makes it what fraction of the whole thing. Okay, so I would just calculate the volume of the whole sphere and then multiply by the fraction. Is it a half of that? Is it 3/4 that? What fraction do you need there? Right? 6 is a subtraction. Right? Hemisphere is taken out of the top, so this dome portion is missing. Okay? And 5 is very interesting. because it looks like they only give you the heights of everything here. But because they stack up perfectly, the radius is exactly the same. The radius of the cone, the radius of the cylinder, and the radius of this hemisphere is exactly the same. So see if you can't figure out what the radius needs to be from the given information. All right, and then 7 and 8, a little wordy, working backwards there. And special bonus for those of you tuning in, okay, I didn't write this down on the Google Classroom post. So only if you tune in and you watched the video will you know that you are allowed to skip 9 and 10 here. Okay? Go ahead and cross those out. We won't deal with those right now, not because they're not good questions. They are really good questions, and I really considered it. But for the sake of time, I don't want to put too much on you all in one day. We'll go ahead and skip 9 and 10 there, as well as 7 on the second page. Go ahead and strike that one out as well. We'll skip that one. We might return to these word problems next semester when we do more of the 3D problem solving. Let's just keep it simple for today. All right? And the surface area questions, again, pretty straightforward. We've got sphere, hemispheres on top of other things. The SAT loves to do this. They can't just deal with one shape. They've always got to combine a shape with another shape, because they test that you know 2 formulas in one question. It's very efficient that way. Okay, so keep in mind your cone. But remember, with surface area, when you combine 2 shapes, one of the sides of each shape is now missing. You don't count this circle in between there. It's not going to get covered in paint. Okay? So don't count that. If you're used to counting the cone as always, oh, this upper area plus the circle, don't add that circle in. Don't add the circle here. Your cylinder only has one bottom circle and the hemisphere dome on top, but don't count that other top circle. All right, this one's going to be the toughest, okay? The cube is easy. The little hemisphere, top is easy. Don't count that circle underneath. So you got to find out a way to how to get, you still need these little corners here. Those are included. But the circle underneath the dome is not. All right, any questions on today's work? Show the formula again. Sure. Should be in your notes somewhere, but there you go. I'll just leave that one on screen and leave the rest to you.